So if we start with just the idea of scanning probe microscopy, in the absolute most generic form of a scanning probe system, we have a probe tip, a probe or a tip as it might be called. That tip is connected to a positioning system, and we have a sample of interest. So this is a microscopy technique. It's going to let us collect an image, and that image is related to the probe-sample interaction. Okay, so the probe, the tip of this probe that interacts with the sample generates a signal of some kind, and that signal then we feed back into the positioning system and use that to collect an image. So we'll scan this tip in the X and Y plane, controlling the height and the Z to collect an image that's related to the probe-sample interaction. And this is a really common thing that you might be familiar with from scanning tunneling microscopy or atomic force microscopy, or in large the lion's share of techniques that make use of this type of approach. In 1989, Hansma at UC Santa Barbara introduced us to a new version of scanning probe microscopy called scanning ion conductance microscopy, and that's the topic that we'll cover today. And so in scanning ion conductance microscopy, the probe is this pipette, and the sample is bathed in an electrolyte solution. That gives us some unique advantages and some of the applications of SICM that are completely different than what you could consider in other scan probe platforms. So if that, thinking about scanning ion conductance microscopy, is the nanopipette probe itself. Again, these probe substrate or probe sample interactions. And that SICM can perform. So this is the generic picture of SICM. This would be a more specific cartoon related to SICM. So with SICM, we have a pipette, a nanoscale pipette, shown here in this cartoon. The pipette's filled with an electrolyte solution. So this sample is completely immersed in solution. It's an in situ technique. We're not in vacuum or in air. There's an electrode inside the pipette and an electrode outside the pipette, and a potential difference is applied between these two electrodes. A current of ions then flows through this pipette tip based on the potential it's applied, and this current is what's measured typically in the feedback loop that goes to this control circuit. Okay, so the position of the pipette then can be controlled in the X, Y, and Z dimension with this piezoelectric positioner, which essentially holds the pipette and moves it at very high spatial accuracy. Now, this in the middle is a cartoon of SICM. On the left is the actual SICM instrument. So the pipette shown here is the pipette here in the image. It goes into this holder that holds the pipette. This electrode is connected through this external wire, and then there's a second, the counter electrode is this silver chloride electrode that's here in this bath solution on the exterior. The piezoelectric positioner is shown here, mounted, the pipette's mounted to that, and then our sample in this case is at the bottom of this petri dish. So everything's in situ in this measurement. Okay, so the first thing that we should think about then, the first thing that one might want to think about is the nanopipette probe itself. That turns out to be a pretty interesting tool, and actually it's a big advantage for SICM. And so nanopipette probes then you can make with a simple puller. We use a laser puller like the one shown here. It's a P2000 made by Sutter Instruments. There are also a number of other kinds of pullers that don't require a laser. We use a laser because we use quartz probes typically, and a laser is required to reach the temperatures to soften the quartz to allow us to pull it. If you use tips like, if you want to make pipettes out of borosilicate or softer glasses, you can use a simple thermal resistive polar. So what happens is the CO2 laser shoots the capillary that's held between the two arms of a polar bar. Those polar bars separate, and it gives us two nanopipettes in one single action. And Sutter's really optimized the system so that you can control these parameters very reproducibly. The parameters of the pole can be controlled very reproducibly and give us tips that are very symmetric, small, and useful for scanning ion conductance microscopy. So if we look at what the probes actually look like, what's shown here are a series of scanning electron micrographs. So the top row is scanning electron micrographs. The bottom row is a scanning transmission electron micrograph. So there's three capillaries that we've pulled into nanopipettes shown here laying on their side. In the middle is an end-on view of a single barrel nanopipette. And what you can immediately see is that this opening diameter, the opening dimension of this tip, can be quite small. So this is on the order of 20 or 30 nanometers, which is putting us in the ballpark of some biological assemblies. And that by itself has some interesting caveats associated with it. The other thing that you can do in addition to just pulling a pipette that has a single barrel is you can add additional barrels. So pipettes with 2, 3, or 4 barrels can be pulled. And if you do that, it gives you two barrels. Each of those can be electrically isolated. So you can do one thing with one barrel and a second thing with another barrel. That turns out to be pretty powerful for a lot of advanced applications of scanning ion conductance microscopy. And then on the bottom is a transmission electron micrograph, so we're shooting through the pipette in this case as opposed to looking at the outside of it. And you can see the wall thickness of the pipettes shown, and inside's the hollow interior. And these are all different pipettes. So the advantage of this is really how easily and simply you can fabricate pipettes. You can routinely make small tips, and then it's cheap. So each of these capillaries costs on the order of $1 if you're using quartz. So in a few seconds, you end up getting two symmetric tips that are roughly 50 cents, which is much cheaper than a technique like atomic force microscopy and the cantilevers required. It's more comparable to the case of scanning tunneling microscopy, I guess. And then the tips themselves have interesting nanoscale properties. Because the tips have a nanometer scale opening, that opening approaches the size of the electrical double layer at the tip, and that leads to some interesting phenomenon. I'm not going to talk about making use of any of that phenomenon today, but it's something that people, or my group for instance, has exploited in different applications. And so those pipettes are sort of the simplest version of a probe tip for scanning ion conductance microscopy. You can actually make a lot of much more exotic kinds of tips, and this is an example from a paper that we published where I just sort of show some of the diversity in tips you can make. And so these tips make use of a capillary. For instance, here we have a capillary that's been embedded in polydimethyl siloxane, and that capillary was coated with a conductive film prior to being embedded. We then overcoated that with an insulating layer, and so that gives us a probe then that has this needle-like geometry. And so this needle is a conductor on the outside, an insulator, it's a conductor here at the base and an insulator at the tip, and this gives us another extra electrode that we can use in a different kind of imaging format. We can also make ring electrodes, ring disc electrodes. These two kinds of electrodes are typically what we'd use for SICM measurements. And we can also make an electrode like the one shown here. So this electrode is a very useful electrode for scanning ion conductance microscopy. It has a a pore in the center of the probe, an insulating glass sheath, and in the outside has a conducting layer on that lines it. It's then again circled by an insulator, and so this conducting ring here then gives us a second electrode that we can control the position of for SICM measurements. So that's the probe for SICM. It's relatively straightforward. What might not be as straightforward as the probe-substrate interaction and how that generates, how that's used to generate the feedback mechanism for SICM. So if we think about the probe-sample interaction and how that's generated, we can start with just a pipette. So here's a cartoon schematic of a nanometer of a pipette. There's no scale here, but in this case it'd be a nanometer scale pipette. It's filled with an electrolyte solution, and then there's an electrolyte solution on the outside too that isn't shown. The resistance of this pipette is a function strictly of the dimensions and the geometry of the pipette. So how far or how long this narrow shank region of the pipette is, what the inside diameter of the pipette is, and what the outside diameter up here at the the pipette diameter here at the top is. So that governs the resistance to the flow of ions or the flow of fluid through this opening when we apply an electrical potential. So what happens if we bring this tip close to a surface? Well, if we bring the tip close to a surface, a second resistance is developed. And that resistance is a resistance we call the access resistance, RAC. So RAC then depends on how close the tip is to the surface, the inner diameter of the pipette, and then the outer diameter of the pipette. And so essentially what we're making then is a situation where the total resistance that we're measuring is the sum of the pipette resistance plus the access resistance that develops because of this gap. This gap then, or this region here right at the tip, becomes essentially a sensing zone, and that sensing zone then is responsible for generating feedback or for measuring the property or for making measurements with SICM. We can define this then as a distance-dependent ion current. So I, as a function of D, is related to the potential that's applied here, shown as U, divided by the total resistance, where the total resistance is a function, again, of the pipette resistance and the access resistance. And it can be related to the geometric properties of the pipette, as shown here, RO, RI, and D, RO, RI, and H, as well as D, the separation between the tip and the substrate. So the important points here then are that probe sample separation is comparable to the size of the probe radius. So the space between the pipette and the sample then approaches essentially the radius of this tip, and that directly influences the resolution that one can attain, and so it's an important factor to keep in mind. Another important point is that the pipette or the probe never actually touches the surface. So it's a non-contact imaging method, a true non-contact imaging method. The pipette essentially hovers over the surface because it never has to physically interact to generate the feedback loop. And then the other thing to remember is that the dynamic changes that one observes as a function of the probe sample distance, which you're really measuring in that case, is you're measuring the resistance or conductance, which is 1 over the resistance, that's changed at the tip of the pipette. So you're measuring the geometric change that happens as the pipette essentially squeezes the space between the tip and the substrate. You're also measuring, possibly could be measuring any local changes in conductivity that happen under the tip. And we've done some experiments like that, and I'll talk about those in the electrochemical talk in a couple of months. Okay, so with that in mind, we understand the nanopipette probes, how those probes interact with the sample, and what leads to the feedback mechanism. Let's talk about the different feedback modes that exist. Okay, so there are typically three classes of feedback modes that are used. There's straight, or what we call DC feedback mode. DC feedback mode, we call it DC because it's direct current measurement. The pipette's approach to a surface and essentially translated then in the XY position, where we keep a constant separation or a constant gap between the pipette and the surface. we can look at this in a plot a little bit more accurately, or easily to see. If we look at the distance between the pipette and the surface as a function of the pipette radius relative to the current, the DC ion current that we would measure through the tip. And what you can see is that if we're far away from the tip, here distance is far away relative to the pipette tip radius, the ion current is essentially doesn't change as we move the tip closer to the surface. Now, when we get very close to the surface, this current falls off precipitously. This is exactly what you want for a scan probe technique. You want a nonlinear response as the tip gets close to the surface, and we can use this then as a feedback loop. So what we'll do is we'll tell the software that I want to set the distance at a certain value, and that value then correlates to a current. That current is something that we can measure, and so we can then input that current value as some fraction of what the maximum ion current is into the feedback loop, and that allows us then to keep the tip essentially positioned over the surface at a constant tip sample separation. Now, DC feedback is by far the easiest feedback mechanism to understand, but it's also maybe not one of the more useful. And the reason why is because if you image for a long time, the composition of the two electrodes that you're using change. So a constant applied bias between this electrode and this electrode will eventually result in drift at long times between these two electrodes. That drift then influences what the set point you chose was, and you can essentially either drive the tip up where it doesn't, if the current drifts, you can drive the tip up where it's not engaging the surface anymore, or you can drive the tip down where it crashes into the surface and you damage the tip. So DC feedback isn't a mechanism that's typically used in, I guess what I would call routine, or especially in higher resolution imaging. The other two methods that are much more useful, and again, the one thing I'd like to add to this is my group didn't develop any of this. I'm telling you about developments from other research groups, notably this AC mode was reported first by Korchev, but even that's related to other techniques that have been developed for other scan probes, like scanning electrochemical microscopy. So in AC feedback, what happens is we're again doing this exact same situation. So I'll show you if you look at the inset, you'll see that there's a probe surface distance and the DC ion current that's measured as a function of that distance, just like for DC feedback. But what we do instead of keeping the tip at a constant position is we oscillate the tip around a distance. Right? That vibration then, that oscillation, if you're far away from a surface, that oscillation generates no change in the current, the modulated peak-to-peak current that you measure. If you get close to the surface, though, small changes in this displacement lead to large changes in the modulated peak current. And so if we measure the magnitude of the modulated peak current, you can see that that current goes up. And we can use this modulated peak-to-peak value then as the value that controls our feedback loop. And this is a much better measurement. One reason why is because now we're making a measurement against essentially a zero background. So we have very low signal. If we're far away, the signal goes up. That's always an easier measurement to make. The other reason why it's good is because we're just worried about what this modulated value is. We're not worried about the overall value of the ion current. And so that makes this much less susceptible to drift. And it lets you do things like probe systems for a long time and do some high resolution imaging. The other mode, and this is really kind of a family of modes that are useful. These are probably the most useful modes presently, are a class of modes called, that are all based on essentially taking successive approach curves at unique positions over the sample. And so calls this approach retract scanning. Other places call this hopping mode or backstep mode. They're not all exactly identical. They're all a little bit different, but they all work on basically the same principle. And so in these modes, instead of taking the tip from a high point into a low point and engaging the surface and keeping the tip close, what we do is we take the tip from a high point to a low point, we engage the sample at some set point, then retract the tip back, reposition the tip, and reapproach. And so by doing that, we can do a lot of much more complicated sample geometries. And the reason why is because we're never worried about the feedback response. We're never limited. We're not limited as much, is a better way to say it, I guess, by the feedback response, because we're always starting from a high point and moving to a low point. And so the tip will never just run into something as it's scanning at a distance close to the surface. The other way that you can take advantage of this is you can essentially take pixelated maps of the entire region that you want to scan and figure out what the entire surface topography is at essentially a very low resolution mode. So if you can do a low resolution pre-scan, then you can readjust the resolution to match the scan resolution and rescan at a higher resolution. This proves to be extremely useful for samples with complicated topography. It's been used to do things like really complicated neural fibers and bundles, collagen fibers. It's a really nice technique. And so some of the data that I'll show you at the end is data that we took with the Park SICM using this approach retract scanning mode. Okay, so that gets us essentially to the situation where we understand the measurement that we're making. We have a nanopipette with these two electrodes in it. We understand that this tip sample separation is what's controlling our feedback loop, and we know what the different kinds of imaging modes might be. The big question then becomes is what is SICM good for? So what can you do with it besides take pictures? And really that's where SICM's sort of had a big push, I would say, in the last maybe 10 years. So a lot of people used SICM initially because you could take very interesting high resolution images. But in more recent times, it's become obvious that SICM can do much more than just take pictures. You can make electrochemical measurements or measurements of biological systems that have some really interesting, give you some really interesting advances. So in terms of biology and SICM, I'm not going to spend hardly any time talking about this today at all. And the reason why is because that'll be a subject, again, of a future webinar. So the one thing that you should think about if you're interested in doing SICM on biological samples is that SICM is unlike other imaging techniques in that it requires that there's an electrolyte solution necessary to generate the ion current. So you have to have this electrolyte solution present for SICM. And physiological buffers are at the concentrations 150, 100 millimolar, somewhere in that range. They're just at the perfect range essentially for SICM. So it works very well for imaging. Other techniques, for instance, something like STM is really difficult to use under this kind of conditions. AFM it's more difficult than typical AFM. It's manageable, but SICM is really geared to do this kind of measurement. And you can see an image shown here on the top. This is an image taken by Park. This is a bundle of collagen fibrils, and you can really see here the advantage of using this kind of approach retract scanning. So this sample has a lot of depth. There's a lot of different layers here that it would be hard to image, and the topography changes very rapidly. So you can see that the rise time is very quick. It'd be very difficult to measure something like this with this kind of resolution, either to probe the depth with a tool like AFM, or if you weren't using approach retract scanning, if you were using these other imaging modes that I talked about, it'd be hard to get the depth in these quick topography changes. This image on the bottom is an image taken from my research group. This is a layer of epithelial cells. In the epithelial cells shown here, we make electrochemical measurements here. Here's a cell body, here's another cell body, and you can see here's the junction between cells. And so we've zoomed in here. You can zoom out and see this layer of cells easier. But if you zoom in even further, we can see, for instance, the microvilli, these small finger-like projections that extend at the surface of this cell layer. And so the resolution here is on the order of 100 nanometers. We can see very nice spatial information in this kind of sample. The cell's alive. It's under physiological conditions, so the cell's happy and it's functioning as it should biologically. So that's an advantage of SICM for making these kinds of biological measurements. The sample essentially can operate under near native conditions. The other place where SICM has some advantages is in making measurements related to energy. And so again, in energy measurements, by energy measurements, I'm talking about things like batteries or fuel cells. An electrolyte solution is also required, typically. Sometimes it might be a solid electrolyte, but often it's a liquid electrolyte that's required to generate the electrical power. That same electrolyte solution, SICM can often make use of. So there's a good match then between the experiment and the application here. And so this turns out to be, is turning out to be especially powerful, I think. So today what I was going to tell you about here in the closing minutes is an application of SICM that we've pursued, and that application makes use of a combination of scanning electrochemical microscopy and scanning ion conductance microscopy. So this is a hybrid imaging technique. We've modified a Park scanning ion conductance microscope to make concurrent electrochemical measurements. And so that's what we'll demonstrate today. SECM is extremely powerful by itself, and you don't have to operate SECM in an SICM, SECM-SICM hybridized mode. The problem with SECM is it's a little bit more difficult to generate a robust feedback loop. The other problem with it is a lot of times we'd like to measure an electrochemical species or an electrochemical process, and we don't want to couple the measurement that we're making to the feedback loop. So what we really need is an auxiliary signal or a secondary signal, and that's what SICM provides. It lets us decouple then the electrochemical measurements or the reactions that are really of interest in these energy applications from essentially controlling the probe position at nanometer scales. Okay, so with SECM then we can measure the electrochemistry that's happening in the sample, and with SICM then we can keep very accurate position and control of where the pipette is in space. And that's important because what we'd really like to be able to get at is making nanoscale measurements, nanoscale SECM measurements, where we understand processes at very high spatial resolution. Okay, so these are the tips that we employed for these measurements. These tips are similar to the tips that I showed you on the slide earlier. We start with a quartz pipette. We pull it to an opening diameter of tens of nanometers. This is a scanning transmission electron micrograph of a pipette, and this is one pipette that we carried all the way through the process. We take that quartz pipette, we then thermally deposit 10 nanometers of chromium, which serves as an adhesion layer for the quartz, and then we overcoat that with 250 nanometers of gold. Okay, so we end up with a quartz pipette that on a portion of it, and this is just by a line of sight deposition, on a portion of it has essentially this gold film that's adhered with the chromium layer to the quartz surface. We then, and that's shown here in this electron micrograph, you can see the gold layer. This is a STEM image again, so we're trying to shoot through it. We can't go through the gold layer, so the gold layer is here on the outside, and the quartz is here on this side. The electron beam's going through it. We then overcoat this gold-coated pipette with a layer of dichloropxylene. This is commonly called parylene. Okay, so we overcoat this entire assembly with parylene. And you can now see here's the gold layer shown here. Here's the parylene layer that's overcoating the gold layer, and then you can see a portion of the quartz pipette still is obvious here. Okay. So now we take this assembly and we move the pipette into a focused ion beam. And what a focused ion beam lets you do is essentially do nanoscale sculpting. And with the nanoscale sculpting, what we can do is essentially chop off the end of this tip. So we can cut the tip here at the end and expose this gold layer. So now we have a central pore. This pore is useful for doing SICM, and this electrode that's in a crescent shape, this gold crescent electrode that's on the outside of the pipette, can be used for recording Faradaic electron transfer. So here in the center we can measure ions, potassium, chloride, things like that, moving through the pipette. We can measure direct electron transfer here at the gold electrode. And here's an electron micrograph for the final assembly. Here's our pipette in the center. Here's the crescent-shaped gold electrode on the outside. Here's the parylene coating on the exterior. Now the reason why we want to use the parylene coating is because we want to isolate the Faradaic electrode at the tip right where the SICM electrode is. Okay, if we didn't put this coating on the outside, the electrode would run all the way up the entire body of the pipette, and we'd measure the electrochemical response from everywhere on the pipette as opposed to just the tip. Okay, so this is the electrode we're going to use to do SECM. This is the inside pipette is what we're going to use to do SICM in this case. Okay, so how do we hook this up in an SECM-SICM setup? So the first thing we do is we hook up essentially the SICM part. I apologize for my phone ringing there. The first thing that we do is we hook up the SICM part. Okay, the SICM part makes use of essentially the central pipette barrel. It has again the pipette electrode inside, the pipette electrode outside. We're applying a potential between those two electrodes, measuring a current, and this current then is going to the feedback loop that controls the pipette position. This again is an approach-retract mode, so we're doing approach-retract scanning here, and we're applying about 100 millivolts here between these two electrodes to generate the ion current for feedback. These are silver chloride electrodes, in case you're curious. Now the other thing that we do is we hook up to that gold electrode on the outside. We hook up the SECM portion. So we have a potentiostat then, and we only need a 2-electrode potentiostat here. We need a working electrode that's this gold layer on the pipette, referenced to a ground, and that then goes into the auxiliary analog to digital converter on the SICM control electronics. So in this type of experiment, the data that I'll show you at the beginning here is for the reduction of ruthenium hexamine. Okay, so with ruthenium hexamine, you can start with no current as you sweep the potential out to about minus 500 millivolts in this case. We get a good reduction current, and we'll measure this then, this applied potential at a constant potential of 0.5 volts. Minus 0.5 volts, so minus 500 millivolts, and this lets us monitor then the electrochemical processes that occur due to ruthenium hexamine at the pipette tip. Okay, so just to recap, the final configuration then has all of these together at one time. We're using SICM to control the probe substrate distance, and we're using the SECM channel hooked up to the auxiliary channel of the SICM input to record the electrochemical information at the pipette tip. Okay, so what happens if you do this? We can start with the example of a gold finger electrode. I'll show you two examples of how SICM-SECM functions. So we have a gold finger electrode, and that finger electrode has regions that are in where there are gold strips or glass or quartz strips. If we move the pipette, if we take the pipette then and we use this pipette hooked up in this combined mode to image, if we're over a gold finger, we can redox cycle, or we will electrochemically cycle if these two electrodes are biased at suitable potentials. We'll electrochemically cycle ruthenium hexamine between these two electrodes. If we then move the tip over an insulating portion, the ruthenium hexamine doesn't get regenerated here at the tip. Okay, so we end up measuring very low currents due to the electrochemical processes of ruthenium hexamine. And you can see this in the images shown on the right. The top image is a topography image that's recorded by SICM. So this is the actual topography of the tip picking up and down as it moves over the finger electrodes. The image on the bottom is what you see in the electrochemical response. So this is a current that's measured at the gold electrode under these conditions. So this is the oxidation reduction then of ruthenium hexamine. If we bias that electrode at a non-suitable potential, so we go to 100 millivolts as opposed to minus 500 millivolts, in the electrochemical signature we see no current response. So what that tells us is that we're really measuring the electrochemical activity over these finger electrodes. So there's no response in this situation, and this shows you how, although we would still record the topography with SICM, we'd see no electrochemical response. And that shows you how powerful this technique is for decoupling then the electrochemical signal from the ion conductance signal for making these kinds of measurements. The other thing that we can do with this, and it's much very similar to what I'll show you in the application, is we can measure the flux of species through a polymer membrane. And that's pretty interesting for a number of reasons. Here what we've done is we have a cell where there's a membrane that's suspended, and that membrane then separates the two solutions. In the top solution there's no ruthenium hexamine. In the bottom solution there is ruthenium hexamine, and ruthenium hexamine is diffusing then through these pores in the membrane. And what you can see in the images on the right, you can see a topography image that's recorded with the SICM in the SICM channel, and here are two unique pores in the membrane. This is a polyimide membrane. The pores are about 100 nanometers or so. And if you look at the topography image, you don't see anything over the pores, but you do notice this feature here that's to the left of this top pore. If you look at the ion current image, though, we can readily observe the diffusion of ruthenium hexamine through these pores in the membrane. And the other interesting thing is, because there is no electrochemistry, specific electrochemistry at this divot or this feature, we're not measuring the electrochemical electrode. So this is a way then that SICM and SECM can be decoupled again to make this kind of measurement. So where can we apply something like this? This becomes interesting if we think about the membranes in fuel cells. So in a fuel cell membrane, we're often trying to convert chemical energy into electrochemical energy, and we have, again, two halves of a cell that are separated by some electrolyte membrane. That electrolyte membrane has specific chemical transport properties, for instance, transporting protons selectively from the anode to the cathode side. A typical fuel cell membrane would be made of something like naphthalene, and the chemical structure for naphthalene is shown here, where chemical selectivity is imparted through these sulfonic acid head groups. All right, so naphthene's good mechanical barrier, and it shows high proton transport. Naphthalene, though, is prone to degradation due to attack from radicals. And so understanding the heterogeneity then in the chemical composition and transport properties of a degraded membrane is necessary then to improve these membranes and how they function. So we performed a study where we intentionally added hydroxide radical species through Fenton's reaction. And Fenton's reaction is shown here at the top, where we chemically decompose peroxide into an anion and a peroxide radical. That peroxide radical then can attack the naphthalene membrane, and it generates these defects. And what you can see is with time, you generate small defects, but as that membrane is exposed for longer and longer times, the defects become larger. This happens due to radical attack, the hydroxide radical attack here, presumably at this alpha fluoroether, which then cleaves the sulfonic acid head group from the naphthalene chain, and then that process can be further exacerbated by further decomposition and instabilities in the remaining portion of the naphthalene chain. Now, you might wonder why this matters that much, and the reason why it matters is because the sulfonate group is what imparts cationic or proton transport selectivity to naphthalene, and it's critical for the operation of the membrane. As soon as you start losing these sulfonic acid head groups, you lose membrane function. So we can take a membrane like this that's been decomposed, and we can do essentially XPS that's spatially resolved at these scales. And so what we see, if we look, for instance, at a region out here where there isn't a defect, we notice that there are two carbon species present. So we're probing the elemental carbon states. And we see two peaks, one at 292 and one at 284 in the carbon 1s spectra. If we look instead over a defect or a bubble, we see that carbon signature changes dramatically. So now the peak at 292 decreases, the peak at 284 increases. And we can assign that to specific chemistries, but I'm not going to do that today. We can also take, for instance, XPS maps. So we can take essentially a picture, and you can see that in the defect regions, there really is a pronounced difference in the ratio of the carbon at 292 to 284. So the take-home message here is that techniques like scanning electron microscopy and X-ray photoelectron spectroscopy tell us that the membrane's damaged and that there's a difference on and off the defects. And that tells us that there's a heterogeneity then in the chemical composition, and that heterogeneity increases again on these defects. The advantage, though, that SICM-SECM has that it can provide in this instance is that we can make an in situ measurement, and we can correlate that measurement directly then to the transport properties of the membrane. So this is the experiment that we'll do. It's the same as the experiment that we did in the case of polyimide, except instead of putting a polyimide membrane here, we'll mount these degraded naphthalene membranes, and we'll watch ruthenium hexamine as it diffuses through this defects or these bubbles and rips and tears that are happening as a function of time. And the one thing you should remember here is naphthalene, ultimately what we're interested in is proton transport, so we're measuring molecules larger than protons. But a selective chemical probe could be developed that would let us directly probe proton transport. Here's what we see when we do experiments like this. After 3 hours of degradation, if we look at the SICM image, and then on the left and on the right's the SECM image, in the SICM image, you can see the topography is changing wildly. We can see these features, these bubbles and divots starting to appear, but really there's no change in the membrane performance at this point, presumably, and that's at least with respect to the transporter ruthenium hexamine. There's not very much action happening in the electrochemical image. As, however, we go to 6 hours, now these features become more pronounced, which agrees with what we see in the electron micrographs, scanning electron micrographs. And we also start to see the appearance of ruthenium hexamine coming through the membrane in unique features. The other thing you'd notice is that not all features are conductive. So there's a defect here and here, and those defects don't show up in the electrochemical image. If we go farther and farther out to 12 hours, now the membranes really started to decompose a lot, and we're getting a lot of background current as well. The other thing here that I didn't point out is we're using approach retract scanning, and that's really critical for this kind of measurement because the topography is varying so much while we're making this measurement that it's really necessary to have the capabilities that approach retract scanning provide in measuring the large heterogeneity in topography. So the take-home message here then is that with SICM-SECM, we have the opportunity then to measure in situ micro and nanoscale transport properties of these Nafion features. We can track the degradation process, and in the future, we can correlate that to membrane performance and use that then to direct us in fabricating more robust Nafion variants of Nafion and Nafion materials. So today, I think that's everything that I wanted to cover, and I'm about out of time. So hopefully, we talked about these operating principles of SICM. I gave you a taste of what SICM is good for in biology and an energy application, and really SICM in general provides us with a very versatile tool then for in situ analysis, and it opens us up to new modes of investigation that are difficult to perform in any other method. So it's a very good complementary technique or primary characterization technique for a number of systems in biology and energy applications. And so with that, I'd like to thank you for coming today, and I'm happy to answer any questions if anybody has any.